general relativity, step by step. Let's look at the line element in Schwarzschild coordinates. I'll just pinch in a bit. ds squared equals minus dt squared 1 minus 2m over r plus dr squared over 1 over 1 minus r plus r squared d omega squared, and I'm going to set that equal to 0. What I'm going to do is I'm going to consider fixed r as well. So in terms of your black hole, you are at a fixed distance from that black hole and you're just sitting there. So that's going to be 0 as well. So we've got that ds squared equals minus dt squared 1 minus 1 over r, where I've made the identification 2m equals 1, simply because it's a pain in the neck to write it over and over again. And also this 2 messes things up because you keep on thinking it's a power and well, anyway. Now what's ds squared? Well, that's going to be equal to minus d tau squared plus dx squared plus dy squared plus dz squared. What I'm doing here is this t equals Schwarzschild t, which happens to agree with regular time far away from the black hole. But what happens close to the black hole? Well, if we're fixed, then these guys are equal to 0 as well. And so what that gives me is that minus d tau squared, this of course being proper time, equals minus dt squared, which is Schwarzschild time, 1 over 1 minus 1 over r. So that says that d tau equals dt times the square root of 1 minus 1 over r. I guess technically there are 2 roots to this, but we are going to consider tau as being the time-like variable. We'll be outside the black hole anyway. So d tau equals dt root 1 minus 1 over r. Well, there's a few ways of thinking about this. What this means is that there's a time dilation effect. D tau equals dt root 1 over 1 minus 1 over r. Let's say r equals 2. And that means that d tau equals dt over the square root of 2. So d tau equals dt times about 0.7. And this is a gravitational time dilation effect. I've actually glossed over a little bit of detail here, and I'll show you what I've done. I've made a sort of tricky assumption. Here's my diagram again. We're going to emit from here, and we're going to receive. Let's try this one. Receive here. So we emit something, and we receive it. Is it that one? Yeah, it's that one. So at radius 2, time equals 0. Schwarzschild time 0. Sends out a signal, and it gets picked up here. At r equals 2, you wait 1 unit of time, and you send another signal in. What I'm saying here is that that time difference there, these are equal, that equals that. Why? Because the metric is stationary. There is no time dependence in that metric. And so if he continues to send signals at every unit of time in Schwarzschild time, simply by looking at the diagram you can tell that that distance there is going to be equal to this distance here. So that's a hidden assumption which I've made, which is not always true, and we'll see later that when we consider non-stationary metrics that this assumption is not justified. Let me go back to my calculations here. Maximize that. There we go. And so we've got this nice relationship here between d tau root 1 minus 2m, I guess, over r times dt. So there's the relationship between Schwarzschild time and proper time there. Now it looks like, well, it's true that if r equals 1, d tau equals 0, or r equals 2m, I guess, times dt. So it looks like for any tick of time, for any amount of time in Schwarzschild time, it looks as though you're going to have no proper time at all at messing. So something odd again is happening at r equals 1. What precisely that is rather difficult to see, because we do not have the nice feature that the graph is continuous at r equals 1. At r equals 1, the light cones close up completely, and so that makes it very difficult to figure out what's going on physically from this diagram. It's a poor choice of, it's a great choice of coordinates out here, because light does what you expect it to do, and here it's all a bit weird. So fundamentally what I'm saying is that a black hole makes it, or at least this set of coordinates makes it very difficult to consider what happens far away from the black hole, and indeed simultaneously consider what happens close to the black hole. And that's really what we're suffering from. Yeah, I'm gonna stop there. I'm going to stop there. Stop. Stop. How do I stop?